Now that we've finished our review of the real-time clock calendar, we'll move on to our next new peripheral, the Parallel Master Port, or PMP. The PMP grew out of the Parallel Slave Port that you may be familiar with from earlier PIC microcontrollers. The PSP allowed the device to be accessed as a parallel device to facilitate communication with a host processor. Using the PMP as a master gives you the ability to address external parallel devices, which we'll cover in the next few slides. The Parallel Master Port provides a flexible 8-bit interface to external peripherals and memory. It supports both Intel and Motorola 8-bit interfaces. The module supports flexible address and data multiplexing to allow optimum use of the I/O pins. Both 8 and 16-bit data operations are supported on the 8-bit parallel bus. The 16 address lines allow the PMP to access up to 64 KB of memory space and can be expanded beyond 64K by using general-purpose I/O pins as the upper address lines or chip selects. One thing to note is that the PMP is used as an external data interface. It is not capable of expanding the program memory for instruction execution. Some features of the PMP are an address bus that can extend up to 16 bits, 8-bit parallel data bus, and 2 address lines that can be configured as chip selects or address lines. The module also includes an address auto-increment, auto-decrement function for fast data transfer, and programmable address data bus multiplexing. Each and every control signal of the PMP can be individually enabled or disabled using bits in the PMCON and PM-enable registers. The control signal polarity can also be individually configured through additional bits in the PMCON register. CS1 and CS2 can be configured either as chip select signals or address pins. This is done by configuring the CSF1 and CSF2 bits in the PM control register. The table below shows the pin function with respect to the CSF bits. The ability to disable control lines and select signal polarity was implemented to reduce external circuitry and conserve pins. The address pins can either be individually enabled or disabled. Depending on the mode, the data is transferred through separate data pins, or the data can be multiplexed with address to conserve pins. Let's look at how the PMP can interface with some of the standard parallel peripherals. The mode bits in the PM mode register allow the PMP to be configured to operate in 2 master modes and 2 slave modes. When mode 1 and mode 0 bits are configured to 1-1, the PMP is configured to interface with Motorola peripherals and LCDs. In this mode, the read and write signals are controlled on the same pin, and a third pin is used as enable. When mode 1 and mode 0 are configured to 1-0, the PMP can be used to interface with Intel peripherals and memory devices, and the read and write pins are separated. To interface with slower memory, wait states can be introduced through the wait B1 and wait B0 bits in the PM mode register. This slows down the signals through the PMP module. The PMP module can also be configured in 2 slave modes. It can be configured as a legacy slave module, like the PSP module in a PIC18, or an enhanced slave mode. In the enhanced slave mode, a 4-level buffer is provided for both data out and data in. The buffer is implemented in the PMD in and PMD out registers. In the legacy slave mode, there are no address lines, but the 4-level FIFO can be enabled by setting INC M1 and INC M0 bits to 1-1. As with the RTCC, much of the initialization for the PMP can be accomplished through the Visual Initializer. The PMP is found under the External Interface heading in Visual Initializer.